Welcome to today's webinar. The topic today is stability design in steel construction with RFEM and RSTAB. My name is Andreas Hörold. I am responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, press releases, the German and English webinars, etc. I will be the presenter today. My two colleagues will support me with answering your questions. They can introduce themselves.
Yeah, hello. I'm also happy to welcome you for the quite interesting topic today. My name is Frank Sonntag and my job is doing sales, trainings and also technical support in the company. So in case of any sales related questions afterwards, just send me an email. I will contact you. Okay.
Hello, and my name is Oliver Müller. I'm a product and customer support engineer at Dlubal Software. And today I'm happy to answer your questions during the webinar.
Okay, thank you for your introduction. We can switch off the webcams that the attendees can see the full screen. On the right side of your screen, you can open a control panel or a panel where you can ask questions here via chat. Oliver and Frank will answer you. As already mentioned, in the case that we get too many questions during the webinar, and we can't answer them, you will get an email after the webinar. The other way is to watch the entire webinar and then email your question to info@dlubal.com. To the agenda today, the first step is a comparison of the different methods. I use a table here in the PowerPoint slides that you can have a good overview. You can also download the PowerPoint slides after the webinar. I will show you how to do that at the end of the webinar. And the second step is applying these methods using examples. I do that in RFEM using different add-on modules. That's the table. I think it's a good overview about the single methods. We go through that table here line by line. First line, equivalent member design according to 6.3.1 of the Eurocode. Name is uniform members in compression. It's necessary that the component is uniform. You can calculate or design all cross sections, but the load can only be compression. An example would be a hinged column or a compression member, for example. Okay, second line, equivalent member design according to 6.3.2, uniform members in bending. The components must be uniform as well. It's valid for all cross sections, but the load must be or can only be bending about the principal axis. Third line, equivalent member design according to 6.3.3, uniform members in bending and axial compression. Also here, the component must be uniform and it's valid for all double symmetric sections. The loads can be compression, moment or bending about the principal and weak axis. Fourth line, general method according to 6.3.4. This method is also valid for non-uniform components. The cross section must be single symmetric. and the load can be compression and bending about the principal axis y. And the fifth line, design according to second order analysis with 7 degrees of freedom. With this method, all components, all cross-section, and all loads, including torsion, is possible, or it's valid for all these conditions. But maybe in additional information, it's necessary to define all the 7 degrees of freedom in the add-on module, and also define local imperfections. But how to do that, I will show you in the program. I will only compare these 3 methods. It's difficult to compare, for example, a column with a bending member, and therefore I compare only these 3 methods. I think the first 2 methods are quite clear. Another overview: necessary add-on modules. You need the add-on module Steel EC3 for all 3 methods. For the equivalent member design and the general method, it's possible to do an elastic and a plastic design. How to define that, I will show you in the add-on module. For the design according to second order analysis with 7 degrees of freedom, the steel warping torsion add-on module is necessary. It does an elastic design. If you want to do a plastic design, you would need the steel plasticity add-on module additionally. Okay, that's all to the overview. We turn to the program RFEM. A simple steel structure. I could only also use RSTAB. It would be the same workflow, but in this webinar, I use RFEM. The construction is stiffened in X direction by frames and in Y direction by bracings, here in the roof and in the walls. Okay, there's only one load and one load combination. I apply the load combination because it calculates according to second order theory. That's the default setting in RFEM and RSTAB. You can also change that option, but the default setting is calculation according to second order theory. The loads are only in vertical direction in the first step, and I applied also imperfections here. Okay, then I show you the set of members that I already defined. The horizontal beam of that frame here, I would like to design the first frame here, because in a later step I will add loads in Y direction to get bending about the weak axis. Okay, horizontal beam, column 1, column 2, and another set of member with the whole frame. I will apply that set of member for the general method. For the equivalent member method, I will apply these 3 set of members. Maybe in additional information about the equivalent member method, the application is for straight set of members. The low truss inclination here is not considered here. Okay, I think that's all. We can go to the add-on module. At first, I will apply the equivalent member method. I'll rename the case. Equivalent member method according to 6.3.3. Okay. I select the load combination 1 and I choose here the general settings of the European standard, not any of our national standards, means CEN. Okay, then sets of members. The left column, the horizontal beam, and the other column. Okay, 1, 2, 3. Then I go to the details settings. Here, as you can see, elastic design. If I select that, the add-on module would be an elastic design for cross sections class 1 or 2. We do a plastic design in that webinar. Next, mask here or dialog, I choose here the equivalent member method. Okay, that's all. Then we can turn to the next dialog. Yeah, we use the same material as in RFEM, same cross section. It is a welded cross section. The height is 400 millimeters, the width 150 millimeters. The flange is 50 millimeters and the web 10 millimeters thick. Okay, next dialog, intermediate lateral restraints. Yeah, we would like to apply supports perpendicular to the weak axis set of the cross section. At the end of this member, 2, at the end of this member, 3, and at the end of member 4. Okay, to do that only one time, I check here, set input for members number 2 to 4. And then I can select here the lateral restraint. 1.0 means at the end of the member. And we can define a lateral and torsional restraint, lateral the lower flange or lateral upper flange. But I select here user defined because I would like to consider a support here in the upper quarter, 100 millimeters from the upper flange means 100 millimeters over the 0 point of the coordinate system. Okay, I uncheck here the restraint about axis X. We would like to define only a support in Y direction. And here an eccentricity minus 100. Okay, it's defined now for all 3 points. That's all. Effective length. First line is the horizontal beam, and second line and third line the 2 columns. For the columns, I can leave the buckling length as the member length because I defined imperfections on them and calculate according to second order theory. Now, that's a valid rule. What I need to do is to define here another buckling length. I enter here 0.25, and now the buckling length about axis Z is divided by 4, and now it's only 3 meters. The 1.0 here means a lateral and torsional restraint at the end of the member or of the set of members. Okay, that's all. Now we could here define or consider shear panels or rotational restraints by trapezoidal sheeting or purlins, but in this webinar I don't want to consider that, but it would be an option. Okay, then I calculate all. We get a design ratio of 65%. Go to the graphic. That's the design ratio, the horizontal beam and the columns. Okay, then we choose here a new case, and I name it general method according to 6.3.4. Okay. Same national annex, same load combination, but this time for the set of member, I choose the whole frame. In that case, I will define the supports here at the single points. Okay. Detail settings. Yeah, we do a plastic design, and for the stability analysis, we apply the general method. Okay, we can skip that dialogues. We can also skip the intermediate lateral restraints. We define all here in the set of members. So we start. I click that here, local coordinate system. And we start with the column basis. Lateral support in Y direction. That's okay. But rotational restraint about axis Z. Okay, now there's a lateral and torsional restraint at the column basis. Then by clicking here, select nodes, I select the single points for the horizontal beam. Okay. And I would like to consider only a lateral support in Y direction and no rotational restraint. Okay. You can see it here in the graphic. I think it's a quite good tool. What we need to define is the eccentricity minus 100, and I can copy that in the next line with F8. Okay, next dialog. We don't need to define anything here. We defined all in the set of members as the nodal supports. Also here, I can calculate all. Okay, I get the design ratio of 68%. we can take a look at the mode shapes. Here's the mode shape, and I believe there will be a lateral torsional buckling in that area here. And what you can see good is that the horizontal beam supports the column by a lateral and torsional restraint, and vice versa. That means that the column supports the horizontal beam by a lateral and torsional restraint. Okay. Then we can leave the dialog or the add-on module. Here you can see the design ratio of the equivalent member method and here of the general method. Yeah, these are two different methods. Don't expect that you get exactly the same results for both methods. Those are approaches to the reality, and you can't expect exactly the same results on the single points. Okay, we turn back to the PowerPoint slide. We compared the equivalent member design according to 6.3.3 and the general method. Our structure has got uniform components. Cross-section, the cross-section is in I-section, and we've got loading, compression, and bending about the principal axis. And if we add horizontal loads in that case, and we get bending about the weak axis, only the equivalent member design is applicable. That's what we do now. I create a new load or add a new load, member load in Y direction, -1 kilonewton per meter. Okay. And then I calculate R, and we will get only results for the equivalent member method and not for the general method. Let's take a look at the graphics. Here, the equivalent member method, we get a design ratio of 68%, slightly higher than before because of the horizontal load. It means the bending about the weak axis. And for the general method, we don't get any results. We go in the add-on module. There's a warning message, moment about z-axis. And that's the reason why I don't get results for this method. Okay, we go to the next structure or next model. Now, nearly the same structure, but now we've got here tapered beams. The height of the cross section here in the middle is 300, here 500, also for the column 500, and at the column base 300 height. Okay, the rest is the same loads, same imperfections, and we go to the add-on module. But before I enter here anything, I go back to the PowerPoint slide. Now we've got non-uniform components, and therefore we can only apply the general method and not the equivalent member method. Okay, back to the program. Same settings, load combination, CEN here, set of member 4, the whole frame. So again, okay. So details settings, plastic design as well, and we apply the general method. I rename the case. General method according to 6.3.4. Okay. Then next, we can skip that again. Cross section. Now, as I mentioned, we have now different cross sections. The height of 300 in the middle of the horizontal beam at the column base, and at the edges of the frame, height of 500 millimeters. Okay, next dialog, we can also skip that. Then we define the nodal supports again. Rotational restraint about axis Z. And then for the horizontal beam, the same workflow as before. Okay. Only lateral support in Y direction. Okay. But what is different here? The eccentricity, because of the different heights of the cross sections. Minus 150, minus 100, minus 50, minus 100, minus 150. So that's all. We can skip that dialog and also that dialog, and we can calculate all. So we get a design ratio of 71%. Take a look at the mode shape. Now, a similar mode shape as before. And that's the design ratio. So we go back to the PowerPoint slide last time. Tapered beam means non-uniform component. Cross section in our case here is an I section. At the moment we've got compression, and y means about the principal axis, and if I add bending about the weak axis, then the general method is not applicable anymore. Okay, that's what we try. Member load, again in Y direction, -1. Okay. And now we get the same warning message. As you can see, no results again. And the warning message in this case here, moment about Z-axis on tapered beam. That's the reason why we can't design this structure here. what we need to do now is to apply the warping torsion analysis. Therefore, I copy the case and name it warping torsion analysis. Okay. Yeah, we use the same settings, but in the detail settings, I need to activate here the warping torsion analysis. I must check this here, perform warping torsion analysis with 7 degrees of freedom. Second order analysis, and we apply the load at the upper flange. Okay, the rest is okay. We can skip the dialogues. But now you can see here, we need to define the 7 degrees of freedom for each support. We start with the column base here. Support in X, Y, and Z direction, that's okay. But about axis X. X, okay. And on the other side, the same, about X and not about Z. So for the support by the bracings here at the edge and so on, I define only support in Y direction. Okay. And since we copied the case, the eccentricities are correct. So we can skip that. But we have to enter imperfection here, means a pre-camber. I go back to the PowerPoint slide. Pre-camber, imperfections for lateral torsional buckling. The formula for the pre-camber is key multiplied by E0D, and the recommendation for key is 0.5. Means the formula is key multiplied by E0D. Table 6. Our structure has got welded eye sections. H to B is larger than 2 in our case. Therefore, we need to apply the buckling curve D. Next table, table 5.1, buckling curve D. The warping torsion analysis is an elastic design, as I already mentioned. Therefore, we need to apply not L divided by 150, but L divided by 300. Because of the formula 0.5 multiplied by E0D. L divided by 300. Go back to the program. 300 and calculate all. Yeah, and we get a design ratio of 95%. Let's take a look at the mode shape. Similar mode shape as for the other methods, but now with double bending. Okay. And yeah, if you want to do a plastic design, you need to activate here under the detail settings, plasticity. I activate that here and go back to that dialog here because The only thing I need to change is the pre-camber. I go back to the PowerPoint slide. Buckling curve D. Plastic design now. L divided by 200 because of the formula 0.5 multiplied by E0D. Okay, I enter that 200 and calculate all new. Now we get a design ratio of 71%. And that's the graphic. Okay, that's all to the examples. I hope you got a good overview. You can download both models and also the PowerPoint slide. How to do that, I will show you soon. But before I do that, I would like to introduce you some free online services. For example, the GeoZone tool with a lot of snow, wind, and seismic zone maps of different countries. The cross-section properties, also a free online tool where you can also define parameterized cross-sections and calculate its cross-section properties. Then the FAQs and knowledge base, a lot of valuable articles. All of them are for free. Just try the search for keywords and you will get valuable articles that you can read. Then the models to download. You can find there the webinar models and also a lot of other models. I can show you it on our website. The YouTube channel with the recorded webinars and a lot of interesting videos. Our web shop is with prices. You can create your own offer as a PDF, for example. We are very open with our prices. Then you can download our trial licenses if you want to try different programs or add-on modules. The trial licenses of RFEM and RSTAB contain all add-on modules. You can also download trial licenses for the standalone programs, RWind Simulation, ShapeFin, Craneway, etc. If you don't already registered for our newsletters, you can register on our website that you can or that you get valuable information with tips and tricks, news about Dlubal Software, webinars and other events. Just register there. Okay, I go to the website. You will get an email where you can get the link to the webinar, today's webinar, but you can find it also under news and events and webinars. Here's stability design. Here you will find the recording the next days. You can already download the presentation slides and also the both models. If you would like to find other models, you can go here to downloads and info, structural analysis models for download. A lot of different models of steel, timber, concrete, membrane structures, etc. You can see there are already over 700 models. Okay, under webinars, you can also see the next webinar, the Dlubal Info Day. If you are already registered for our newsletter, you will get an invitation next week. a whole day about Dlubal Software with different topics, design of steel and membrane structures using our form finding and our wind simulation, design of reinforced concrete floor slab, design of a cross-laminated timber wall element, etc. And you will also get tips and tricks about our software. Okay, I turn on the webcam again because I would like to say thank you for your attention. Thank you to my colleagues for answering the questions. And maybe an additional information when you leave the webinar, there will be a short survey with 4 or 5 questions. I would appreciate it if you answer the questions, or you select if you liked the webinar. The worst score is 1 and the best score is 5. That's maybe an important information. Okay, then thank you for your attention. Have a nice day. Yeah, and bye-bye.